morning and welcome to YouTube channel of Lucky Institute of Professional Studies. I, Mamta Arora, will today be discussing about deadlock in operating system. So let's just first find out what is deadlock. I will try to explain it with a real life example. Like we are going on a road and we are on a crossing where there are two other people who are waiting to cross the road. So what we'll have to do, we'll have to wait for some time for the second person to cross, and then only we'll be able to cross. So in this situation, or we can say this situation is known as deadlock situation. When we come to operating system, there are n number of processes which are waiting for the task to complete. So they want various resources to complete their task. When they are waiting for n number of resources, let us say if process P1 is waiting for resource R1, if process P1 is waiting for resource R1 and this resource has been held by process P2, then this situation is known as deadlock. So there are four necessary conditions we need to look for deadlock. First is mutual exclusion. Second is hold and wait. Third condition is no preemption. And fourth condition is circular wait. Let us discuss with mutual exclusion. Mutual exclusion means that once any process has taken one resource, it will not release the resource until and unless it completes its task. And what it says is one process can take one resource at a time, can hold only one resource, and all the resources are in non-shareable mode. Then hold and wait, it means that once any process has taken any resource, then it will not release the resource until and unless it completes its task. For example, say process P1 is waiting for resource R1, or it has already holded the resource R1 and it also needs resource R2. So P1 will always keep R1 with it until and unless it gets the resource 2, and then it will release. Then it will only release the resource R2 once it has completed the task. Third is no preemption. No preemption means once the task has been started, the resources will not be released until and unless the task has been completed. Circular wait. Circular wait we can understand by a diagram. Let's say we have process P1, we have process P2, we have process P3. This means process P1 is waiting for process P2 to complete, process P2 is waiting for process P3 to complete, and P3 is waiting for P1 to complete, right? So this is all about deadlock conditions, four conditions. These are the four necessary conditions which are responsible for deadlock to occur. Now today we are going to discuss here how we can avoid deadlock. Deadlock avoidance. I am going to discuss deadlock avoidance with an algorithm that is known as Banker's algorithm. What does Banker's algorithm mean here? Banker's algorithm is an algorithm in this, OS will first only decide how many resources are needed for any process to complete, and once it acquires all the resources, then only it will start doing its task, so that we can avoid the deadlock situations. I would like to explain this with an example. So today we are going to see deadlock avoidance. In deadlock avoidance, we are going to see Banker's algorithm. In Banker's algorithm, we have following statistics given. What Banker's algorithm states that when we have to avoid deadlock, we have to first only tell what resources are to be used or required by all the processes, so that when we'll have those instances of resources which are required, then only the process will go into the execution state. We have whatever the resources are allocated to all the processes. This A, B and C here means there are various instances of which number of resources are given. Then what is the maximum requirement of these resources, of these processes, of these resources? Then next is available resources. Now what we have to find out is what is the actual need after the allocation. That we can find out after subtracting the allocation part from the maximum need. Let's see how we can do it. The maximum need of process P0 is 2 and the allocated is 1. So what we'll do, when we'll minus max minus allocation, we'll be getting the need matrix. What is the actual need? So 2 minus 1 is 1, 2 minus 2 is 0 and 2 minus 0 is 2. Then 1 for process P1, let's check what is the requirement. 1 minus 1, 0, 1 minus 0 is 1 and 0 minus 0 is 0. For process P2, 1 minus 1, 0, 4 minus 1, 3 and 3 minus 1 is 2. Then for process P3, 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1 is 0. Next for process P4, 1 minus 0 is 1, 2 minus 0 is 2 and 2 minus 1 is 1. Process P5, 1 minus 1 is 0, 5 minus 0 is 5 and 1 minus 0 is 1. So this is the current requirement of every process which process needs what resources are given in the need matrix. Now what we have to do, we have to check a sequence of processes which will not create a deadlock. We will find that whether this process or the sequence which we are going to find out will create a deadlock or not. So let's start how we will find out. This is the availability and this is the current need. We will be checking that to which process we can give these available resource so that it can execute. After the execution of that process, what will be the new availability? It will be whichever process has executed, it will release its allocated resources, which will then be added to this available resources. Let us see how. The availability is 0, 1, 0. Instant A has 0 resources, instant B has 1 and C has 0. Let's check what is the requirement. As soon as we see that process P0 requires 1 of instance A, whereas the availability is 0, we'll move forward. Then we'll see for process P1, 0, 1, 0 and availability is also 0, 1, 0. So what we'll do, we'll give this available resource to process P1 so that process P1 will execute and then it will release its resources. So to write the safe sequence, what we can do is, first of all, we'll execute process P1. So here we can write the safe sequence. First process which is to be executed is the process P1. After executing P1, what we will see, this allocated resources will later be added to the previous available resources. So it had 1, 0 and 0. So the new available resources with us are 0, 1, 1. So this is the new availability. Now because we have executed process P1, let us strike so that we don't check it again. Then next availability is 1, 1, 0. Let's check process P0. No, its requirement is more. Let's check process P2. Its requirement is more. Let's check process P3. Process P3 needs 1 instance of A, 0 instance of B and 0 instance of C. So need should always be less than or equal to available. So here what we can do is, we can execute which process? Process P3, because its need is less than what resources are available. So next in the sequence we will be having is process P3. Once process P3 finishes its execution, the resources of P3 will be added to the available resources. So 0, 1, 1. 0, 1, 1 will be added here, and new availability we will be getting is 1, 2 and 1. So again, let's strike the process P3 because it has completed its execution. Next, we'll again check. We'll start with this process P0. No, it can't execute. Again, process P1, P2, it can't execute. And let's come to process P4. Yes, the need and the requirement, need and the availability is same. So what we'll do next in the sequence will come process P4. Now, what is the next step? All the resources which are held by process P4 will be released and it will be added here 001. So the next availability, the fresh availability or the new availability, what we will be getting is 1, 2, 2. Let's try process P4 here. Okay, next we will see, is this fulfilling the requirement? No. Let's go back to P0. P0 needs 1, 0, 2. Yes, we have available resources. Then we'll write in sequence P0. Let's add whatever resources P0 will free. It will free 1, 2 and 0, 2, 4. The resources will be released is 2, 4. So, and what we have done, we have taken P0, we have added the resources, and what we will do is, we will strike P0. Next, the availability is 2, 4 and 2. Let's check. We have only 2, P2 and P5 remaining. So, P2 need is less than what we are having available. So, what we will be doing is, we will be executing next in the sequence P2. Then P2's resources which are held is 1, 1 and 1. Let's add. So new availability is 3, 5 and 3. So what we can do now is, now we have last resource process available, that is whose requirement is 0, 5 and 1, and the available resources are 3, 5, 3. Yes, we can give them. What we will do is, we will give them and the sequence will be P5. Next in the sequence we can add P5. It will again release its resources, that is 1, 0, 0, and finally we have these resources available with us. Fine. So when we are able to get this safe sequence, that means the complete task or these all processes after execution, the system is not in a deadlock state. So here we have taken an example where the system is not in a deadlock state. In next video, I will be sharing with you an example in which we will see that system is in deadlock state. Thank you. Have a good day.